Good morning. First of all, I would love to welcome you back. Hope you are safe. Today, we will tackle the second online lecture about the functional programming paradigm. We will be tackling today the topic of data types. Okay, let me recall what we did so far last time. If I want to define a data type in Haskell, then what we need actually to do is, if it is not just a renaming of, let's say, an existing data type, we will use actually the data keyword. Thus, let's assume we want actually to define a data type which is called a list. Now, once I have a list, it's actually I'm having a collection of data that I want to store in a specific data structure. And the first question that I have to ask myself is, what will be the data type of the element that I want actually to store in the list? Okay, thus the data type could be a list of integers, it could be a list of floating point numbers, it could be a list of strings, it could be a list of Boolean values in this case, and that's why what I will be defining here is I will define a data type which is a polymorph one. Thus the list will have as a data type an element, okay, of type A. Okay, thus the question is define a list. Okay, now we did it already in Prolog. Okay, a list could be either, if you want actually to define it, can be defined in an inductive way, in a recursive one. It could be either empty. Thus, in this case, I will be using the keyword nil. Okay, this is just now a constructor that defines that the list is an empty one. And the second case is that the list consists of at least one element. And in this case, I want actually to build the list in this case. Thus, in this case, I will be defining something of type, a constructor which is called cons. Okay, and I want to define a list that consists of at least one element. That this element will be of type A, and the rest, okay, of the list will be a list of type A in this case. Thus, I will be defining the whole thing in a recursive one, and you can read it here. A list, okay, of elements of type A could be either a list which is an empty one, which is denoted with nil, or a list that consists of one element, which is the hat, and a tail list in this case, and this list has to consist of elements of the same type A in this case. Okay, thus, once I have this data type, I can define, let's say, some of the functions. I will define a function which is called length, okay, in order to avoid the problem, because the Haskell prelude has already a predefined function which is called length. I will be giving the name of my function length too. Thus, if the list is an empty one, then it's of the form nil. I know exactly an empty list will be having 0 elements. If the list is not empty, then the list will consist of at least one element. Thus, the whole structure will be the following. It's cons. X, this is, let's say, the first element, and then you are having XS. Well, XX is the tail list. In this case, it could be either empty or a list that consists of at least one element and a tail list. Thus, it's just the recursive definition in this case. Thus, once I write cons X XS, the X is the first element of the list, and the XS, in this case, is the tail list. Now, what will be, in this case, the result of the length of the whole list? Okay, that's for sure the first element will be counted as 1, and what I have to do is I have to call the method length2 recursively on XS in this case. Thus, the length of a list that consists of at least one element corresponds to the length of the tail list plus 1. Okay, now once I will load this one, okay, you will go, and what you can do is you can just check the length of nil. In this case, what I'm expecting here is I will expect 0, and you get actually 0 as a result. And the second thing is I will build a list that consists of, let's say, 2 elements. Then the list will have cons of 6, and then cons of 7, and last but not least, nil. Okay, in this case, the total number of elements will be 2, because I'm having 2 elements, 6 and 7 in this case. Okay, and the nice thing is, if I have, let's say, 6.2 and 7.3, Okay, the list is a list of floating point numbers, and what you will be getting here is you will be getting actually 2. Now what you can do is you can actually have a list of in this case strings. Thus if I have hello, and instead of the 7.3 I will be having word, in this case the length 2 will work, because actually the data type of the list is a polymorph 1 and the total number of elements will be 2 in this case. That's the question is, what will be the data type of the length? Okay, thus I will actually define it myself. However, you will see that Prolog will be able actually to perform a better data type in this case. Now the length will have something of type list. Okay, this is actually the input. It takes one parameter. Okay, it's of type list, and it returns actually something of type int in this case. Now once I will compile and I will just reload the file, it's an illegal one because the list is a list A. Okay, then in this case what will happen here is that if I will ask about the type of length 2, you will be getting as a result, okay, exactly the data type that you defined, which is actually a list A int. Now the question is, if I wouldn't have done that, what kind of result would Haskell infer as a data type of length 2? Now I will go, okay, I load, let's say, my file again, and I will ask about the data type of length 2. Okay, Haskell will outperform the data type that the user defined. Thus it will give always, okay, the most general data type of the function in this case, because if you take a look at the operation that I'm performing here, it's an operation 1 plus. Thus 1 plus meaning you are actually performing the addition of a number. The number is of a numeric value, okay, to another one, okay, which is at the end of the day it will reach actually the 0, and that's why Haskell will be able to provide you with the most general actually data type, which is actually the following, that this it's a numeric value, okay, which belongs actually to the type class num in this case. Okay, a numeric value could be either a floating point number or in this case an integer in this case. Thus if you compare actually to the two different actually data types, you see that the one that the user actually defined is more specific than the one that Haskell will be able actually to infer, and that's why we will always actually give the upper hand to Haskell to generate the most general data type for functions in this case. And you have to know that this data type is always the most general one that can be inferred. Now without going into details, what Haskell does is something called the unification algorithm, okay, just to be able to find, let's say, the most general data type in this case. Here I will give you the idea of the algorithm itself. Now the length 2 takes, let's say, as a first parameter something, okay, that has a value nil. Thus Haskell knows automatically that nil can only be of type list A in this case, and that's why the list A can be inferred from actually the first one. And now once you are having actually a 0 or let's say 1 plus something, Haskell will know exactly that the data type of the result will be actually of a numeric value, because if you will go and you will ask about the data type of 0, okay, you will get actually that the 0 is of type A, where the A is actually of a numeric value in this case. And this is exactly how the type inference engine works in Haskell in this case. Okay, now this was just a recall about the data type of list in this case, and what we want actually to do today is we want actually to rely on the data type which is already predefined in Haskell, which is the list 1. Okay, yes, I will actually start to give you an idea about how the list will look like. Okay, the list can be just written as follows. An empty list is a list which is denoted with 2 square brackets. Okay, and if I'm having a list that consists of few elements, in this case 1, 3, 4, 5, then you just actually delimit the elements or you put actually the elements between 2 square brackets in this case. Now let me go and tell you exactly how the list is built in Haskell. Now this cons in Haskell corresponds actually to the colon 1. Thus if I am having 1, Okay, then what I can do is I can have 1 colon empty list. Okay, this corresponds to cons of 1 nil. Thus, in this case, what will happen here as a result, we get actually the singleton list 1. If I want actually to have 1, 2, 3, and then colon an empty list, then in this case I will be having 1.2, 1, 2, 3 in this case. Okay, thus the representation of 1, okay, in this case colon 2, colon 3, colon an empty list consists, okay, of the following representation if I will rely on the definition of the list that you see here. Okay, now what will be this representation? It's cons of 1, okay, cons of 2, cons of 3, and last but not least nil, in this case 1, 2. And once you will have it, I will be having actually a problem. Why? You saw it last time, because actually this one has to be transformed into a string in order here to be displayed. And that's why what I need actually to do is here to write something like deriving show. Okay, in this case where the show function will be always applied on term before actually it gets displayed in this case. Now once I will go here, once I will go and load and call actually the cons of 1, cons of 2, cons of 3 and nil, you get actually the representation displayed here as we expected, where the colon corresponds actually to the cons constructor and the nil corresponds actually to the empty list in this case. Okay, that's starting by now we will be relying on the representation 1, 2, 3, 5 in this case, okay, to represent a list. And the representation is that actually a list consists of, if I want actually to have a list consisting of only 2 elements, 1 and 2, then you have actually to have a list which is consisting of 1, 2, colon, let's say an empty list in this case, which is 1, 2. If I have here 4, 5, 6, then the first 2 elements are 1, 2, and the third element will be 4, the fourth element will be 5, and the last element will be 6 in this case. Okay, keep in mind that you cannot have a list, okay, where here you will be having, let's say, something of a different data types. Okay, Haskell will tell you, I'm sorry, I'm having a problem. The list data type is a polymorph one, however, actually the data type is a homogeneous one. Okay, and that's why if you want me to write actually 1, 2, 3, this one will work. If you want me to write 1, 2, and 5, this one will work too, and the 5 actually will be converted to 5.0 without loss of precision. However, okay, and if you want actually to write hello and then word, this one will work without any problems, because the 2 elements are of the data type string, where the string is a list of characters in this case. And if you want actually to do this one with 5, Haskell will tell you, I'm having a problem. The first one is a list of characters, the second one is a list of characters, however this one is an integer, thus the engine will not be able to infer the correct data type in this case. Okay, now let me go to the length function and implement a second one, okay, which is called length 3, that works on the predefined data type using actually the constructor colon as well as the empty or the 2 square brackets actually to denote an empty list. Thus, I will actually define it the same way. However, now we will be relying on the predefined data type in Haskell, which is actually the list data type. Thus, length 3 of an empty list will be equal to 0, and length 3 of a list that consists of at least 2 elements, at least 1 element, will have actually the following form: xs, okay, is equal to 1 plus, in this case, length 3 of the list xs. Thus, the implementation is the same. The only difference is, instead of using the cons, let's say, constructor to define it, we are using the colon constructor in this case, which is an infix notation or predefined in Haskell in this case. Okay, thus, once I will go and I want to load and call the length 3 of, let's say, the list that consists of 1, 4, 5, the total number of elements will be 3. Now the question is, I would love actually to know the data type of length 3. Okay, thus you go back, and what you will get here, okay, is that the data type of the input, okay, argument is a list, the list is a list which is a polymorph one, and that's why you will get actually something of the following form. Okay, the list is a list that consists of elements of type B. Okay, however, the result will be of type A, where the A is of numeric value, similar actually to the one that we had in defining actually the length based on the user-defined data type that you see above. Okay, let me go further and let's think about, let's say, getting the head of the list. Okay, thus, if I'm having a list which is an empty one, okay, then actually there is no head in this case. However, if the list consists of X and anything else, then I know exactly that the head of the list will be X in this case. Okay, thus I will just always give, let's say, 2 as the name of the function to avoid, if the function is predefined in Haskell, then the prelude, in the prelude, then actually I will not have a problem, because actually overloading is not allowed in Haskell in this case. Now, let me go and compile, and what I will do is I will load it, and I will call head2 of a list, where list consists of 1, 6, and 7, and what I should get as a result is 1, and you get actually 1 as a result. Okay, thus the underscore means I really don't care about the result in this case, and that's why here I can replace this one with an underscore because I don't need it, and here the X I don't need it actually to the right hand side, and then actually what I will do is I will, let's say, change it to an underscore, which is actually the wildcard, and once you will load, actually you don't have any problem with that. Now, let me go to call actually the head of 2, which is an empty list. You see actually that an empty list doesn't actually match any pattern in this case, because actually the pattern that I'm having here is a list that consists of at least one element. However, if I'm having an empty list, there is no, let's say, case that will manage that. And what you get here is an error that will be thrown. In this case, it tells you, I'm sorry, you are having a pattern match failure, because I am trying actually to match the pattern of an empty list with the definition that you have, and I don't find actually anything that will match actually this one. Now the question is, what do I want actually to do? Here an error will be thrown. It's like actually exception that is thrown in Java, and the question is it possible to handle the exception in a better way? I will tell you this can be done, okay, with the function which is predefined in Haskell, which is called actually the error function. Thus, the error will expect as an input a string. Thus, I will say, sorry, okay, the list is empty. And if the list is empty, then there is actually no head. Now, look at what will happen. Now, whenever actually I load, what you will be getting whenever you call head2 of an empty list is the following. Okay, I didn't actually save head2. Sorry, it's head2. Okay, and now once I will load and call actually the head2, you get actually as an output, let's say, the error function will display the message, sorry, the list is actually empty in this case. That's it's actually one way how you will handle exceptions in this case. If there is a kind of failure in the pattern matching, the error function can be used in order actually to display a message to the user, in order that the user will know exactly what kind of problem I am having actually in this case. Okay, now let's go to the last element of the list. Okay, thus if I'm having a list and the list is an empty one, then there is actually no last element. That means I will do it actually with the same way. Okay, I will get an error, okay, that the list is empty, and that's why, okay, the first case will be identical actually to the head 2. Okay, the second one is if the list is not empty, then it consists of at least one element. I don't care about, let's say, the value of this one. Okay, however, what I need actually to do is I need actually to call the last 2 of XS. Okay, and the question is, when should I stop? Okay, that's the base case will be that I will reach a list that consists of one single element in this case, which is actually X. Okay, is the singleton value in the list, and what I will do is I will actually display it in this case. Thus, I will be having 3 cases. The first case handles the case where the list is an empty one. In this case, I will be just returning or displaying, sorry, the list is empty. If the list consists of one single actually element, okay, it's a singleton list, then actually I will return the element itself. And last but not least, if I will go and I have a list which consists of at least now one element, okay? And the second, what I need actually to do is I need actually to call the last two, let's say recursively, and the anchor case actually will reach whenever the list will become a singleton one. Now, once I will compile and once I will load, okay, I will try it out with last two of an empty list. In this case, I'm expecting, let's say, an error that will be displayed, and the error will be, sorry, the list is an empty one. Now, if I have a list that consists of only one element, you get actually the 5 as a result. And if you have a list that consists of hello and then word, in this case, what I need actually to do is I need actually to get as a result the word actually word, and you get actually the word as a result, which is the last element of the list. If I do it actually with the third one, okay, hello world today, then in this case what you will get as a result is today, which is always the last list that will be displayed. Now let's go to take a look at the type of last two, okay, and you have actually to look at it. Now, I'm not performing any operation on the list, meaning actually the list will be a polymorph one. It works actually for integers, it works for a list of strings, it works actually for a list of floating point numbers. And here, in this case, I know exactly that the last two will expect as an input list, and the list will consist of elements of type A. And the result, okay, has to be, let's say, something of the same type of the elements in this case. How did, let's say, Haskell find actually this one is just actually by taking a look at the second case. If the list consists of a singleton value x, then actually the result will be returned. That means it's clear that this x is having actually the same data type as this x in this case. And that's why once you will call and you want to find the type of last two, okay, now what you have to know is that last two will have as a data type actually the following. It's a list that consists of, let's say, a polymorph one, okay, and it's a list of A's, and the result actually is an A, which is, let's say, the type of the element in this case. Now let me actually just check whether this is actually the same result that I will be getting. Yes, okay, just actually for your information, this is a comment, that means it's not there, okay, and that's why you are getting actually the same data types in this case. Okay, let's take a look at the following problem. We have a list and we want to check whether a list is sorted or not. Okay, that's the function that we want to implement is a function called isSorted. It takes as input, as argument, a list, and it returns true or false depending on whether the list is empty or not. Thus, if the list is empty, then actually for sure the list is a sorted one. If the list is not empty, then either it consists of one single element or more than one. Thus, let's start actually to handle the case where the list consists of one single element. Thus, I have a list and the list is a singleton one. In this case, I know exactly that the list will be also a sorted one. Now, if the list is consisting of more than one element, then the whole thing actually will look as follows. You are having x colon y. X is the first element, y is the second element, and last but not least, I will be having a rest list in this case. Now, when what I have to do is I have to compare actually the x and the y. And if my x is less than or equal to y, in this case, I will know exactly that what I have to check is whether the list consisting of a first element, which is y and xs, okay, is sorted or not. Okay, thus again, if x is less than or equal to y, then I'm sure actually these two elements are sorted relative to each other. That means what I have to do is I have to check whether y colon xs, this list is a sorted one or not. Now, if x is not equal, less than or equal to y, then actually in this case I know that x is strictly greater than y. Thus, I know exactly that I have to stop, and what I have to do is I have actually to return false in this case. Okay, thus it's a nice, let's say, a function that is consisting of an if-then-else statement. And what I want actually to do is I want to try it out. Okay, let's check different cases. The list is an empty one. I should expect true, and you get true as a result. The list consists of one single element. The pattern matching will go to the second definition of the function is sorted, and what I should get here as a result is true. And last but not least, if I want to have, let's say, a list that consists of more than one element, I will be having 1, 4, 6, and 7. This list is a sorted one, and I should expect true in this case. However, if I have here 70, and as a last element 8, and after that 9 and 22, I know exactly once I reach these two elements, 70 is not less than or equal to 8, and that's why in this case what should return in this case is false. I will go, and false will be returned as a result. Now the question is, what is actually the type of is sorted? Thus, it has always actually to do with, let's say, the type of the x less than or equal to y. Okay, thus I know exactly that in this case, if I want to, let's say, compare actually two elements, I need actually to know exactly the less than or equal in Haskell on which data type will it work. Thus, the data type in this case is a list of elements of type A, where the A should be something that can be ordered, and that's why the subclass of it is order. Okay, and the data type of the output will be bool. That's actually, I see that the Boolean data type is found just actually by looking at the data type of the result here, either true or false. Okay, and the data type of the elements of the list is found through the inference engine just by looking at the x less than or equal to y. Now the question is, if I have, let's say, 1 less than or equal to 3, Haskell will give me a correct result. That means it will work actually for integers. If I have 4.2 less than or equal to 5.6, then in this case you get actually true. That means the class of numeric value is a subclass of ord. Okay, and that's why if I will compare the is sort, if I check actually the is sorted with 9.1 and here 6.3, then in this case you get false, and the is sorted function will work correctly in this case. Now the question is, let me check whether if I am having two string ABC, okay, whether I can compare it with less than or equal, in this case, less than or equal to Z, D, and A. Okay, and in this case what will happen here is I get that strings can be compared with less than or equal. That means the string or the list of characters is a subclass of let's say elements that can be ordered in this case. Thus, if I have is sorted, now what I can do is I can actually compare it with let's say GUC, and then I will be having AUC, then I will be having the GIUAS, and now what I will do is I will compare the GUC with the AUC. The GUC is not smaller than or equal to the AUC. That means in this case I will be expecting false. However, if I will just change the order, if I will be having an AUC is smaller than the GUC, and then I will be having for example the GUX as let's say last element, then I know exactly that the GUC is smaller than or equal than the GUX, and then actually what I should get here as a result is true. Okay, thus if you think about actually the type again is a list of elements that can be ordered, thus either numeric values in this case or strings, which is a list of characters. Okay, and the result will be a Boolean data type. Okay, nice. Let's go further and let's think about two lists, and what we want actually to do is we want actually to append them. I will show you let's say the predefined operator in Haskell. It's ++. You take a list 1, 2, 3, and you take a second list which is 4, 5, 6, and what I want actually to have as a result is the append of two lists in this case. This is already defined in the prelude, and that's why you can actually use it right away. And if you want to implement it yourself, the question is, how can I implement an append one? Okay, please remember that we did, let's say, the append of two lists in Prolog. You can do it in any programming language, because the programming languages that we are dealing with are languages that are Turing complete. Everything that is computable can be solved in Prolog. It can be solved also in Java, and it can be solved in Python, because actually these programming languages, all of them are Turing complete. Now, the question is, how can I implement this one? Okay, just actually for your information, what I need actually to do is, I need actually to do it recursively. Okay, thus, if the list is an empty one, and the result is y, then I know exactly that appending an empty list with any list will give me actually the list as a result. Okay, now if the list is not empty, then it consists of at least one element. That means I will be having x colon ys and y. Now the question is, which element should be put as the first element? Is the x. Okay, that's the x will be the first element of the result list. And last but not least, what I need to do is, I need actually to append xs with the y in this case. Thus, I get the result list and I will append it recursively with the y. Okay, and last but not least, whenever the input, the first input list will become empty, okay, the whole thing actually will match the first case, and I will be returning the second list in this case. Okay, now let's try to run it. Now what I will do is, I will just check it actually with append of an empty list and a list that consists of 1, 2, 3. That's what I need actually to get is 1, 2, 3, and this one will work perfectly, because the pattern matching will hit, let's say, the first definition of the function, and I will return actually y in this case. Now the question is, what if I am having a list which is consisting of 1, 2, 3, and a list that consists of 4, 5, 6? Okay, what will happen in this case? Okay, this one will not match the pattern that I'm having here, because actually the first list is not an empty one. Okay, however, the second list will match actually the pattern, and x will be equal to 1, and the xs will be equal to the list 2, 3. That's what I will do is, I will take actually the list 2, 3, and I will append it with 4, 5, 6. Once the result is done, I will cons to it the x. Okay, thus, once I am done actually with that, okay, the result that you will be getting is 1, 2, 3, 4, 5, 6. That means this one actually will work perfectly in this case. Okay, now the question is, let me check actually the type of append. Okay, now it's a curried actually function, meaning any function which is curried, as we saw last time, is a function that takes only one parameter. That means actually the first thing is, what is the type of this parameter? Okay, this is a list. What kind of elements could it have? It's a polymorph actually list. It can be, let's say, any data type, because I'm not performing any operation on the elements in this case. And that's why here Python will find out that this list is a list of A's. Okay, and now the question is, this y is what? Now, if I take a look at this, let's say, definition, then I cannot say anything about the type of y, because I'm having a list, okay, and a y. This could be any data type, and the whole thing will be equal to y. Taking a look at only the first definition of the append, I cannot say anything about the type of the y. However, what the unification algorithm does, just to find the type of the second argument, okay, will be the following. If I take a look at it in the second line, just actually by taking a look at the left-hand side, you cannot say anything about the y. You can only confirm that, let's say, the first type, the type of the first argument is a list, because it's having the form x cons xs. Now, once I go to the result, okay, Haskell will infer that the outcome can only be a list, because you are having x and you are using the cons operator in this case, and this can only give us as a result a list. Thus, in this case, once you ask about a type of append, you will be getting a list. Okay, append will take as parameter a list A. it returns a function that takes as a parameter, I'm talking about the y, which is also a list of a's. And last but not least, the result will be after appending all elements of type A from the first list with all elements of the second list, and both of them are of type A, then the append can only of type A in this case. Now the question is, if I have that, can I actually do an append of, let's say, two lists, where the first list is a list of integers and the second list is a list of strings? For sure, Python actually will tell you, Haskell will tell you, I'm having a problem. I cannot infer actually this data type, because here the two lists should be of the same type in this case. That's if I will go and take a look at this list and convert it to a list that consists of strings, GUC and GIUAS, then in this case the result what I will be getting is just an append of the two lists, because both of them are lists of strings, and the string is a list of characters in this case. Okay, nice. This is the append one. Okay, just keep in mind, you can always define your own, let's say, data type in this case. Okay, if you want actually to do it, you can only restrict the data type, okay, that corresponds to this one. That means what I will do is, I will say, I want actually to implement an append. The append will take as a first parameter a list of integer. It returns a function that takes as a parameter a list of integers, and the result can only be a list of integers in this case. You go, okay, and you compile. Now, whenever actually you do it, if you ask about the type of append, the type of append change, because now Haskell will comply to the definition that the user wrote. Thus, if I have an append of two lists, 1, 2, 3, 4, 5, 6, this one actually will work perfectly. However, now you will see it. If I want actually to append two lists of strings, this one will not work anymore. Why? Because the user decided actually to have as a type of an append function that takes as a parameter a list of integers. It returns a function that takes as a parameter a list of integers, and the result will be a list of integers in this case. Now, if I will comment this one, then life will be better. I will rely now more on Haskell, and Haskell will tell me, if you want to see the type of append, I will give you the most general type in this case, which is a list. It's a polymorph list. It's a list that has elements of type A. This is the argument of append. It returns a function that takes as parameter a list of A's, and last but not least, the result will be a list of A's in this case. Now, going back actually to the append of the string, this one actually will work further because I commented, let's say, the data type of the append here. Okay, as we saw before, you can always go to, let's say, a kind of definition that the user will implement, which will be always more specific compared to the data type that Haskell will give you in this case. Okay, now let's implement actually the following function. I will just it's existing in the prelude. I will be having a list that consists of 1, 2, 3, and another list that consists of 4, 5, 6. That's actually, I'm having, let's say, two lists, and I want actually to zip them, meaning I want to take the 1 and the 4 and put them in a tuple. It's a pair. I want to take the 2 and the 5 and put them in as a pair, and I will want to take the 3 and the 6 and put them as a pair, and the result will be a list of pairs in this case, where the first pair consists of the first element of the first list and the first element of the second list. The second element of the result consists of the second element of the first list and the second element of the third list, and so on. Okay, thus the question is, how could we implement actually this function? Okay, I will call it zip2 in order not to, let's say, conflict with the prelude zip that is defined in Haskell, and I will write actually the following. What if my first list is an empty one? I know exactly that the result should be an empty one. And the question is, let's take a look at the symmetric case. If the first list is not empty, but the second one is an empty one, then the result in this case should be an empty one too. And last but not least, if I am having a list that consists of, let's say, X and XS, that's the first list is not empty and the second one is not empty either. Now the question is, what should I do? Okay, I will do it step by step. I will take the X and Y and put them in a pair. And I will const the whole thing with zip2 of the rest list XS and YS in this case. This is it. As simple as it is. I will take the X and the Y. I will put them as a pair. And last but not least, I will const them with the result of zipping the rest list of the first list and the rest list of the second list in this case. Okay, now let's try actually to do it, and let's try to first of all compile. Okay, I will compile and then I will call, let's say, zip2 instead of zip. Okay, I should get the same result, and you get 1, 4, 2, 5 and 3, 6. Now the question is just actually by taking a look at the definition, what is the type of this one? Okay, for sure, just by looking at the first, the second, and this first and the second definition, I can actually know exactly that the first parameter is a list, the second parameter is a list, and the result is a list too. But is a list of what? Now, just actually by looking at this one, this list is a list of any data type A. Okay, and this list is any list of data type B. The question is, should they be the same, yes or no? It depends on whether in Haskell I can allow tuples that are having, let's say, different data types. And what I can actually tell you is I can actually have that without any problems. If I take actually 1 and A, okay, 1 is an integer and A is a string, this one actually will work perfectly. And that's why we will know exactly that the zip2, if you want to define its data type, is a list of A's that goes and returns a function that takes as parameter a list of B's, and now the question is, the result is of which data type? Okay, now you have actually to take a look at the result. The result is a pair. The pair is consisting of, let's say, a first element that is having X and Y as, let's say, components of the pair, meaning I know exactly that the X is of type A and the Y is of type B, and the whole thing actually will be put in list. Why? Because I'm consing it with, let's say, a recursive call of zipping the rest list in this case. Okay, thus once I will have that, I will comment it, and just actually for your information, I want to rely on Python actually to find the type of zip2. And the nice thing is, if we are good, then actually we found out in this case the most general type of the function. I can make it always specific. However, if you take a look at the zip2, you will see that actually the one that we commented is identical to the one that Haskell actually found out. And this is exactly what you have actually to do whenever you write a function. First of all, you implement it. Second of all, you have actually to find, let's say, the data type, which should be actually the most general data type that the engine, the inference engine of Haskell will be able to generate in this case. Okay, now let's go further to another function. Now we zipped, now we want actually to unzip. Meaning, let's assume I am having a function that is having 1, 2, okay, 3, 4, and last but not least 5, 6. Okay, and what I want actually to do in this case is to get a list that consists of 2 lists, or a pair that consists of 2 lists as a result, where the first list consists of the first attribute of the pair, and the second list consists of the second actually values of the pairs in this case. Thus, if I do it with unzip, I should get 1, 3, and 5 as a first list, and last but not least, the second list will consist of 2, 4, and 6 in this case. Okay, now the question is, how can I implement it? It's an unzip function. The unzip, I will call it unzip2, and what I will do is, I will just think about the following. What will be the case if the list is an empty one? Okay, I know exactly that the result should be a pair where the first list is an empty one and the second one is an empty one too. Okay, let me check actually the unzip okay, which is the prelude one. Here it's unzip 2, here it's unzip with an empty list. And what I will be getting here is a list of, let's say, pair where the first argument is an empty list and the second argument is an empty list too. Okay, now let me go further and implement an unzip 2, the second actually one, where the first, let's say the list is not an empty one. Now, if the list is not an empty one, then I know exactly it consists of the following. It's a pair that is having XY and just actually a result list L. Okay, now in this case, I know exactly that the first list, the first element is a pair XY. It's actually like the 1, 2. That the 1 should be put in a list and the 2 should be put in the second list. Okay, that's what I know is that the result will be in this case X. Okay, the rest list will be called L1. Okay, XL1 in this case. And last but not least, I will be having, sorry, it's a pair, okay, XL1, and the second one will be, in this case, Y, L2. Now, the only question is, what will be L1 and L2? This is a pair. The pair consists of a list XL1 and YL2 in this case. Okay, now, the question is, what is L1 and L2? Okay, now I know exactly that L1 and L2 should be the result of unzipping the L. Okay, that's what I will do is I will write that the L1 and the L2, okay, it's a keyword which is predefined in Haskell, okay, and the L1 and L2 has to be equal to the unzip 2 of L in this case. Okay, now once you have actually this definition, then you know exactly if the list is not empty, then it consists of at least one pair. I will take the first argument of the pair and put it as a first element of, let's say, the first list, and I will take the second argument and I will put it as the first element of the second actually list. Okay, and both of these arguments will be cons actually with L1 and L2 that I have to compute by unzipping actually the rest list in this case. Okay, now let's go and let's try it out whether this one actually will work. I will go and I will do, let's say, the unzip 2 of a list. Will list consist in this case of the list will consist of a list that consists of pairs. I will be having 1, 2. Okay, I have it already. That means I will actually do the one that we have actually above, but I will change the unzip actually to unzip 2, and I should get actually the same result. And nicely, we are getting actually the same result in this case. Now the question is, if this one is the case, then I can actually have something of the following form: a list where 1 is related to A, 3 is having a relation with the B. That means I will be putting them in a pair, and last but not least, the 5 actually will be put in a connection, a relationship with the C in this case. And now Haskell will tell me I really don't have any problem. You will be having actually 2 lists as a result. The first list is a list of integers and the second list is a list of strings. Okay, thus having actually said that, let us try actually to infer the type of unzip 2. Okay, the type of unzip 2 is a list. Okay, it takes as a parameter a list of pairs. Okay, where the pair shouldn't actually have the 2 arguments shouldn't be having actually the same data types. That means you will be having actually a list. The list is a list of pairs of type AB in this case, where the first argument is of type A and the second argument is of type B in this case. Okay, now if I want actually to take a look at the result is a pair. Okay, and the pair is a pair actually of 2 lists. Now I know exactly that the first, let's say, argument, the first list corresponds actually to the first arguments of the pairs. That's actually, this one should be actually of type A. And last but not least, the second one will be, let's say, the list that consists of the second arguments of the pair in this case. Okay, I will just comment this one, and I will rely again on Haskell, and just actually check whether Haskell will give me the same data type of unzip2 in this case. And nicely, you get actually the same data type. Okay, thus we found out that the type of the function takes as a parameter a list of pairs, where the two arguments shouldn't actually have the same data type. They could, but they don't need to, and that's why you are having two variables. One of them is called A and the second one is B, and the result will be a list of A's and a list of B's, in this case actually put in a pair. Okay, nice. We are almost actually done, except I want actually to show you something about the composition of lists. Okay, as we saw before, if you write actually 1, 2, and then 4, 5, 6, this one actually consists of a list that has as a first argument 1, as a second argument 2, okay, and the whole thing actually will be const with a list having 4, 5, 6 in this case. Thus, Haskell will accept it and will get you actually 1, 2, 4, 5, 6 in this case. Okay, now the question is, what if I want actually to have a list that consists of 1, 2, 3, 4, 5, okay, 6, 7, 8, 9, and 10. Okay, now instead of writing that, there is actually a shorthand of doing it. That's actually what I will be writing here is something of the following form: 1. Okay, and just actually remember what we did in CLP. Okay, in the CLPFD, you are having actually the representation of interval. Thus, if I am having actually from 1 to 10, in this case, you will be getting actually the same result, which is 1. Okay, 2, 3, 4, you are enumerating actually all values from 1 to 10 in this case. Okay, with the difference that actually this one, you can do it even with, let's say in this case, characters. If I do actually AZ, what you will be getting here is you will be getting actually all characters, or all the alphabet A, B, C, D, E till you reach Z in this case. Okay, and if you want actually to do it with, let's say, A and Z, then you will be getting actually, let's say, the whole thing in uppercase. Okay. Now, the question is, what if I want actually to have, let's say, a list with a kind of a jump of 2 elements, meaning I will be having 1, and then I will be having 3 little 10. Is it actually possible? Will Haskell accept it, and what will it actually understand from it? Okay, now what you will get here is you will get 1. The second argument is 3, and here, since actually the distance between 1 and 3 is 2, now the second element will be 5. Okay, 3 plus 2, then 5 plus 2 will be 7, 7 plus 2 will be 9, and this will be actually the result in this case. Look, if I will do it actually 1, 5, and 4, what I will be getting here as a distance is 4. Thus the result will be 1, 5, and the third element will be 9, and actually I am actually done in this case. Okay, now the question is, it works actually for integers, it works actually for characters. What if I will be having something of the following form: 1.5, okay, till you reach 10. Okay, now what you will be doing here is you will be getting actually, you won't actually get all, let's say, floating point numbers between 1.5 and 10, because in this case actually the enumeration will be in infinite 1, but what you get as a result is just actually a jump of 1.5, and then plus 1 is 2.5, 3.5, and please actually take care that the last element can exceed actually the 10. That means if I am having 9.5, okay, the last element that I will be getting is plus 1, which is 10.5, which is actually larger than the upper bound that you have actually here. You have actually to take care that it doesn't stop actually by 9.5 in this case. Okay, now the question is, what would have happened if I will be having actually something of the following form? I will be having 1.5, and then actually the next one will start from 3 till 10. Okay, now what you will be getting here is a jump of 1.5. Is always actually the same, is just a distance 1.5, 3.0. And then for 3.0 you will be adding the distance, which is 1.5, you get 4.5. Then you add actually 1.5, you get 6.0. You add 1.5, 7.0. You will add 1.5, you get actually 9. And last but not least, to the 9, you will be adding a distance, which is 1.5, and you get actually, let's say, 10.5 as a result. This is actually something that you may need, just actually to write a kind of shorthand. It's a composition of lists to get actually a shorthand in this case. Hope you got, let's say, the idea about lists. We are done with this lecture of today, and I hope I will see you soon here at the Jam University in Cairo. Please stay safe, stay home, and we will provide you with some problems online on our MET website in order to practice what you saw today about lists. Okay, thank you very much, and see you soon. Bye-bye.